have a version of the sandwich rule for functions, which is very similar to the one we saw for sequences. So okay, so we have the limit of g when x goes to a is equal to the limit of h when x goes to a is L, and in an environment of a we have this. Okay, so f is bounded from below by g and from above by h. Then the limit of the limit of f when x goes to a is the L, right? And the rule is valid if a is plus or minus infinity and L is plus or minus infinity. Okay. First consequence of this is that when the limit of the absolute value of a function, right, is 0, this implies that the limit of the original function is also 0, because we can bound the function from above by the absolute value, and we can also bound it from below, right? So it's either the function is either smaller or greater than the absolute value, right? Sorry, minus this. It's either minus the absolute value is going to be smaller than. Okay, so if the limit of this is going to 0, right? We have that the limit of this is going to 0, as we have seen in sequences, right? Now, let us see a couple of examples of this, right? So we have the limit of when x goes to 0 of x squared times the sine of 1 over x, right? Now we can't apply the algebraic properties that we have just seen, right? Because the sine of 1 over x doesn't have a limit when x goes to 0, right? You see the sine of 1 over x is this function that we've seen in the exercise, right? It oscillates a lot, and it gets more and more oscillating when you get to 0, right? But we know that the sine of 1 over x is always going to be bounded between minus 1 and 1, right? So if we multiply this inequalities by x squared, we have this. So our function x squared times the sine of 1 over x is bounded by minus x squared and x squared. And if we take the limit of when x goes to 0, this is going to 0, this is going to 0, so the limit of this is also going to 0. Okay, and in this case it's the bounding by the multiplication by this number that makes this function convergent at 0, right? And so we can plot, you have in the lectures the actual plot of this function, but let me try and plot this here. So this is x, and so the x squared looks something like this, right? We've plotted this before. And minus x squared, right? Something like this. Whoop. Okay. Well, x squared times the sine of 1 over x is going to be bounded by this, so it's something like this. This is, oscillating a lot, and then it does something like this, right? Does something like this, and then the other way around. Okay. I'm very bad at plotting, but you see the idea. The oscillations are always going to touch the parabolas, right? Because when the sine of 1 over x is minus 1, then it goes like this, and then when it's going 1, it goes like this, and so on and so forth. Okay. And then let me give you another example here of where the limit where x goes to a of the square root of x is the square root of a, right? If a is greater than 0. And for this we're gonna use again the sandwich theorem. So that when the limit when x goes to a, and we can say that we want to prove this, right? That the difference of this is going to be 0, right? But this is also equivalent to proving that the absolute value of the difference is 0, right? If the absolute value of this difference is 0, that means that the difference is 0, and if the difference is 0, that means that the absolute value is 0, right? So it's the same thing. So we know that in order to prove this, we know that 0 is smaller than or equal than the difference, right? Because the absolute value is always positive. Now we multiply and divide by the conjugate, so we have in the denominator we have square root of x plus the square root of a, and then here we have x minus a, and in the denominator we have positive numbers, so we can, this is x minus a, the absolute value, divided by the absolute the square root of x plus the square root of a. Okay, we have this. Now this is going to be smaller than, because the square root of x is going to be positive around or close to a, okay, because a is positive. So this is smaller than this. Okay, when you have a denominator is greater, this is smaller. And now if we take the limit here, okay, the limit of this is going to be 0. Okay, so the limit of, sorry, let me say this again. We have 0 is smaller or equal than the difference between the square root of x minus the square root of a, which is smaller than this. Okay, now we take limits here. The limit when x goes to a of this, the limit when x goes to a, and the limit when x goes to a of this is 0. Okay, this is 0, this is 0, and so that means that this has to be 0, which proves the original result. Okay, now you can try and use the same argument in order to prove that the limit when x goes to a of the nth root of x is the nth root of a, using kind of the same argument and this identity that we have seen before, and it comes on you know, over and over again, because it's very useful actually, right? So try to do it on your own.